We can take 80-year-old cells from an 80-year-old person and reprogram them to behave as if they were embryonic. Different species of organisms live for different amounts of time. It's kind of programmed into our being. Mice live about 2 years and bowhead whales live about 200. And so that's one evidence that there's a program in there. It doesn't mean it's immutable. It can be changed in principle. It can be changed genetically or to a limited extent epigenetically. We've improved our longevity worldwide on the order of 1 year every 4 years over the last 170 years. So that's kind of steady progress. And we had a slight slowdown recently, due to diet, sedentary life, high medical costs, suicide, addictive drugs. But we haven't really gone that far backwards. It's just a tiny little blip so far, but we need to be very cautious of it. In no way have we gone back 170 years, but maybe we've gone back a year or two. So, but there's a lot of people that who their longevity is greatly affected by their not just their environment, but the genetics that they have, and we need to pay attention to them as well, not just the healthy.
So looking at sort of the whole aging framework, what are the top few things you can think of that are so important to actually prevent disease and live longer? Just curious how you're thinking about it.
Well, so I think a lot of the people that are listening and watching this podcast are already doing everything they can do.
Maybe. I wouldn't assume that.
Exercise and watching your diet, sleeping well, having good social interactions. These are all well known, at least. Whether it's convenient is another matter. But they will plateau at some level that's based on your genetics, environmental components outside of your control. And the genetics can include things that are species specific, like being a human being. That doesn't mean that that's the absolute limit, however, because we have changed ourselves radically as a species. That's why we live almost twice as long now, through things like vaccines and better diagnostics for cancer and better treatments.
Yeah. So from some of the framework of the hallmarks of aging, this was something that's being talked about a lot in the sort of halls of academia and research on aging. And there are things that happen to us as we age that seem to underlie all diseases: DNA damage, mitochondrial damage, trouble with proteins, inflammation, nutrient sensing problems, hormonal dysregulation, microbiome changes, epigenetic changes. And so, there's 9, 10, however you slice them, hallmarks. And there's a lot we're learning about how these phenomena that happen in our body actually are driving all these downstream diseases. So the whole concept of aging is being challenged from just being a normal process to actually being a disease. And the WHO recently created a ICD-11 diagnostic category for aging as a disease. And so can you speak to that concept of aging as disease versus just a normal phenomena, and what we know about that, and how we actually can start to treat aging?
Well, I'm happy with it. However, it's defined. The ICD change is okay, but I think we could have and could still just treat it as a natural process that results in a series of age-related diseases, and then we can get FDA approvals for interventions in that natural process as it causes disease, as either preventative or rapid reversal of those diseases of aging. Almost every major source of morbidity and mortality, especially in industrialized nations, are either due to or greatly exacerbated by aging, even accidental death. Falling down, the probability of falling down is higher, and your probability of not getting up, probability of having bad outcome for an infectious disease, also very steeply age-related. So I think if we deal with the underlying causes of all these age-related diseases, we can stay within the framework of disease.
Yeah.
Without necessarily defining aging as such. to me, it is either way is fine. But we have been in our development of medicines focused on the whatever the FDA considers acceptable.
Yeah, well, but you know, the what's so interesting to me is that you know, David Sinclair and others, you talked about how if we treat the hallmarks of aging, we don't actually have to treat the diseases downstream. So we don't have to treat heart disease, dementia, cancer, diabetes. They're all really one phenomena that manifests, you know, as different branches on a tree, but it's all the same trunk. And so how do we start to attack those things? Because traditional medicines, you know, take statins for your heart disease and do cancer screening, and pretty much for dementia, there's no recommendations other than maybe a healthy lifestyle. Diabetes, obviously, eat better. But I think that there's not really an understanding of how we really start to treat these hallmarks. What is sort of your framework around how we begin to address and treat these hallmarks?
Well, I agree that it's quite likely that if you get at the hallmarks, if you get all of them, you may have to get all of them, because if any one of them escapes, then you will die by that pathway. We know a great deal about each of these 9 or 10 pathways at a molecular level, at a physiological level. We know it. We don't know everything, but we know enough to start the kind of medical engineering process in a big way. But we do have to get all at once. And many of the traditional bits of advice really only get 1 or 2. So they are interconnected. It's like whack-a-mole. You can't let any of them escape. The way that my group has been mostly focusing on this is by restoring a younger internal state. That is to say, from a systems medicine standpoint, you can look at things like the proteins and the nucleic acids in the cell, and if they are youthful on the whole, then the cell will behave as a youthful cell. And if all the cells in your body are behaving as youthful, then you will be, okay? So for example, and this is a very potent example, is we can take 80-year-old cells from an 80-year-old person and reprogram them to behave as if they were embryonic, and probably anywhere in between. But definitely that dramatic change from 80 years old to close to 0 has been proven over and over again as a standard tool in my field. It isn't something you can use clinically, however, because if you changed every one of the cells in your body into an embryonic cell, you would no longer look like an adult. But you can do partial reprogramming. That's called reprogramming. Shinya Yamanaka got the Nobel Prize for it 2 decades ago, but for work that far back. But it shows that it's not just about damage. Those cells can be restored to an earlier state, and then they will. And there's another way of resetting them, which is well known, which is called cloning. You can take a nucleus out of an adult mouse and put it into an egg, and it will develop into a mouse. And then you can take that adult nucleus and do it again. And you can do that 25 times. And you can't just pass it off as, oh, this is selection that the egg and sperm are selecting for healthy, the ones that fix their, So repair is certainly a state of the cell. If a cell thinks it's young, it will repair the damage for the most part.
That's just astounding. So essentially what you're saying is through the Yamanaka factors, which are transcription factors that this Dr. Yamanaka found in Japan years ago and won the Nobel Prize for it, that those factors we have when we're younger, and they tell us how to develop and can help us sort of program our genes to create who we are and which organ and tissue. But by using these, they get silenced at some point in our life, but by turning them back on or inserting them into the cell, and I want to sort of get into how we do that, and then flipping them on, we can literally reprogram our biology back to a younger self. And
that's right.
I've heard David talk about this, David Sinclair, and I'm like, well, this is wild. So how far are we from actually human trials where we'll be able to take these Yamanaka factors, insert them through some technology, which I'd love you to explain, and then turn them on when appropriate. And let's say I'm 62, but I don't want any gray hair anymore. I got a few gray hairs coming in, or I want to, get rid of my wrinkles, or my joints are bothering me. So, it's like, how do we kind of begin to think about that? Is that something that's coming down the pike soon? Are we far away from that? And what are the implications for that?
Well, you can typically get some idea of how close it is to human use if you're going through animal preclinical trials, because those, if they're successful, they lead to human clinical trials, which then lead to broad use if all goes well. So we have animal trials that we've done for both for the Yamanaka, a subset of the Yamanaka factors. They're sometimes abbreviated OSKM, and so we've done OSK is a little safer. And those have been shown in mice. And then we have another set of proteins. These are natural human proteins. We've done another set, which are things like fibroblast growth factor number 21 and alpha klotho, and put those into that's been tested in mice and in dogs. And the dog, this is work, Noah Davidson was a postdoctoral fellow in my lab and now has his own company called Rejuvenate Bio. And and those are a veterinary product now for dogs, which is a good way of really testing it. It's better than a clinical trial because you get people's pets, and dogs have a fairly similar lifestyle to humans. They live in a similar environment. They sometimes eat the same food, and they're loving and they make eye contact and the whole bit. So that's a terrific segue into, I think, even better than primate trials. So those are all moving very very close, and they have been shown. We've tested them initially on 4 diseases of aging. Now it's up to about 7 diseases of aging. So when you're getting all these diseases that have very little in common other than they're age-related, then you're probably getting at the core part of aging. Yeah.
So, these diseases may not seem related, but, they are often driven by insulin resistance, like dementia, heart disease, cancer, diabetes, which are the main things that kill us other than lung diseases, which are usually caused by smoking. Those are all driven by insulin resistance, even increased inflammation that goes along with aging, even the increased risk for infections and decreased immunity. So I think there's a kind of a unifying frame about that, but it seems like these Yamanaka factors.
The diabetogenic part of the hallmarks of aging are just part of it, because if you completely cured cancer and completely cured all these diabetes, like metabolic diseases, you still would have a lot of people dying of age-related diseases. It's been estimated that maybe you'd add 2 years on average to the population longevity if you completely eliminated cancer, and probably a similar thing for the metabolic diseases. So you really have to hit the whole circle of hallmarks of aging.
And you think that the Yamanaka factors are the key to this, or they're just one part?
Well, I mentioned the ones that are furthest along are not Yamanaka factors. The problem with the Yamanaka factors is that they are cell autonomous, which means that you put them in cell number 1, and for the most part, they do not affect any of the cells nearby. Now, a healthy cell will, send off healthy vibes in various forms, protein molecules. But for the most part, you fixed the cell you delivered it to. Okay? Yeah. But these other ones I was talking about, like FGF21 and alpha klotho and TGF beta receptor 2, these are intentionally diffusing out. Wherever you put them, whatever cells you put them in, they will be releasing these molecules into the bloodstream. And so it's kind of like taking a pill every hour for the rest of your life, or eating the right foods, or whatever it is. It's reprogramming you epigenetically all the time. Yeah. And in every cell. And that's the problem with delivery, is if we could deliver to the germline the way we do for some of our animal experiments, pigs, you could affect every cell in the body because they all grow out of one cell.
I see.
But when you're delivering it in an adult, it doesn't necessarily, a gene delivery like the Yamanaka factors do not go to every cell in the body.
Oh, wow. So that's kind of limits what they do. So you have to kind of inject them where you want them. Like, right? If you have a bad joint.
Even if you inject them where you want them, they won't necessarily go to every cell within the diffusion radius of the injection. So delivery is a problem. It's not just where you inject. You can also deliver some of these proteins orally. I mean, they can make it past the stomach acids and so forth. This is not. There are not many examples of this, but you can do it. But anyway, it doesn't matter how you deliver them, intravenously, intramuscularly, or orally. They don't then get delivered to all the cells in your body. And since at least all the stem cells in your body, they also don't get to all of those. So those are, at a minimum, those are what you need to do to really get serious impact on these age-related diseases.
So if you did stem cells, for example, immune stem cells or stem cells for a joint or heart, would that then sort of create the germline that would actually help all the downstream heart sort of cells?
Whatever stem cells you get will then help all its progeny, all the baby stem cells and all the differentiated cells that come from it. But you don't necessarily get all the stem cells. So if you deliver it intravenously, you only get a subset of stem cells. So the rest of them, now you could say, well, the rest of them are going to age and die, and it doesn't matter. So that means the ones you got will then proliferate and take over the job that is, which is fine. So that I certainly wouldn't rule that out as a possibility, that you can deliver Yamanaka factors to enough percentage of each category of stem cell. Mm-hmm. There's no, by the time you're an adult, you don't really have too many pluripotent stem cells that you had when you were an embryo that can produce everything. So you have to get each category. You have to get the blood-producing stem cells, and some of them don't have a lot. So, for example, there aren't that many neuronal stem cells. Yeah, there are a few, mainly in the hippocampus. They're not quite as many cardiac stem cells as one would like. So if you get a subset of something that's already very small, it may not be enough. We don't know. These are really interesting, intriguing possibilities. But I plan for the worst and hope for the best, rather than assuming the best.
I mean, this whole idea of reprogramming our biology to a younger you is really astounding. And what you're saying is now we sort of know how to do it in animals, for the whole animal, right? Mm-hmm. But not in humans. And it's hard to figure out, where the trajectory this is going. I mean, my understanding of the Yamanaka factors is they actually reprogram you to this inducible pluripotent stem cell, which in English means you've got a stem cell that it reprograms it to that can become anything, right? But you're saying that kind of is a little tricky when it comes to humans.
Yeah, it's not that we don't know how to do it for humans. We might know how to do it for humans, but it's going to take a while to get it into clinical trials. The thing that's tricky is delivery, both in animals and in humans. In animals, you have one thing you can't do in humans, which is germline delivery. It's not particularly useful in humans because most of us, almost 8 billion of us, are already past that stage, and we deserve some medical care that will make us youthful longer. And germline's off the table anyway for at least temporarily for ethical reasons.
Yeah, it's challenging. So reprogramming is coming, but we don't know if it's 5, 10, 15, 50 years, right?
Well, I think it's unlikely that it's 50 years. It either will fail for some fundamental reason, which I think is unlikely, or we'll be moving into clinical trials within the next 2 years, or 10, in that range. Is the clinical trials, and it's just there's a lot of different ways of doing this. I think a lot of the more promising ones, at least from my biased point of view, are based on gene therapy, which is really protein therapy with naturally occurring proteins that decrease with age, or possibly some that increase with age, reducing those. So I think we're very close, and I think there's going to be a number of different groups trying different things, and one or more of them will work.
I mean, from a selfish point of view, I'm older. You obviously have gray hair. So is there any hope for us? Are we going to die before we figure this out, or is this coming sooner than our lifetimes are going to end?
Well, literally, if the clinical trials start 2 to 10 years from now, some of us will be in those clinical trials. Yeah. And then if they work, then some of us will already be fixed. So one of the nice things about gene therapy is that in principle, it's once and done. You don't have to be taking a pill every hour for the rest of your life. It's doing that automatically. You've got all the natural physiological feedback loops that modulate it and so forth, and rather than having to like measure your blood glucose and all that.
So you're more excited about gene editing than the Yamanaka factor reprogramming, it sounds like.
No, I'm interested in gene therapy. It doesn't have to be editing. The Yamanaka Factors is gene therapy in that you're moving in 3 or 4 genes into some subset of the cells. What I described, that Rejuvenate Bio is using that, and they're also using a different set of 3 genes, which are like by risk with factor 21, that spread out from the cells more actively than you get. So there's 2 different strategies. One where just fixing a subset of the cells and hoping that they will proliferate and displace the ones that didn't get the gene therapy. And the other one is getting gene therapies where no matter what cells you get, they're going to be secreting the right proteins for life. And those are both being tested simultaneously.
So tell us more about the gene editing and the gene therapy part, because that's a really area of expertise. You helped invent CRISPR, which is the technology for gene editing. So tell us, like, where are we at with that science, and what are we looking for clinically from it, and what's actually happening now, and where are we going?
So gene editing, almost everything I've talked about so far is gene therapy that was not called gene editing. Now, it could be gene editing kind of grows to include everything, but the original gene therapies was sort of gene replacement or gene augmentation, where you're increasing things that have gotten lower. Editing is typically either removing a gene's function or changing it precisely. And it's usually thought of in terms of inherited diseases, where you might have someone with very serious disease like sickle cell or potentially Alzheimer's, something like that, where you go in and change one base pair back to what it should be, what it is in the healthy population. Now, in practice, that again has a delivery problem, but it's a smaller one in that you now have a smaller number of cells that you need to fix. Like it could be like for hemoglobinopathies like sickle cell, you just have to fix the precursor cells, the erythroid cells that produce the red blood cells. So that's, in a way, you have to deliver it to people. In fact, you can take those cells out of the body, like the hematopoietic stem cells, fix them, and then put them back in. So there's a lot of interesting opportunities that come when you're dealing with specific inherited diseases. And that's what editing is good for.
Yeah. So basically you have a gene for like sickle cell anemia, you cut it out, you put in the right gene, and then the sickle cell anemia is gone.
Right.
But the other thing you're talking about is gene therapy, where you're it's like the bionic man. It says you're augmenting a human genome with genes that produce different proteins that have beneficial functions or that reverse aging somehow.
Right.
Can you talk about what that is? Because this is sort of, I think, interesting for people. They haven't really sort of know about reprogramming maybe and gene editing, but this whole idea of gene therapy seems a little bit kind of...
Well, gene therapy greatly precedes most of what we've been talking about. We have been talking about gene therapy. All the things that we're pursuing at Rejuvenate Bio are either Yamanaka factors or these growth factors and you basically can either introduce DNA or RNA, either in a viral capsid, just not the virus, but the capsid, the protein coat, or a non-virus lipid nanoparticle. And probably the thing that most people are familiar with that uses all the same tools as gene therapy, and basically some people call gene therapy, are the new COVID vaccines. That there's one category which is double-stranded DNA in a viral capsid, and another category which is single-stranded RNA in a lipid nanoparticle. And most people have gotten one of those 2 categories, and it is, I think a lot of us probably owe our lives to that particular kind of gene therapy. It's been applied to a huge fraction of the human race, and it has costs as low as $2 a dose. And you really don't need that many doses to have protection. With some vaccines, you have lifetime protection. That doesn't seem to be the case for COVID, but that's not the fault of the gene therapy part of it. It's the virus itself. Yeah, exactly.
It's changing. Yeah. Well, that's fascinating. So, can we imagine a gene therapy to help us recover our memory, or to repair our joints or to improve our hearing. Like I'm like noticing my hearing maybe not as great as it used to be. So like how do these things work in terms of what people suffer from day to day?
Well, it's quite possible that some of them will be very hard to reverse. I mean, for example, if you have an amputation, there are animals that will regrow limbs, so it's not completely out of the question. Or potentially, you could grow a limb in a lab, or and transplant it. We're getting good at transplanting a variety of organs. But many of the other things are reversible, and so there'll be the hair cells that you said hearing. There are hair cells that we lose, but our avian birds do not lose them with age. So that's some gene that got messed up somewhere in the mammalian lineage that was fine in our reptilian and avian brethren. So that might be fixable too if you get it early enough. If you can turn those, if you can turn some kind of stem cell into hair cell stem cells like they are in birds. So there are a lot of things that seem like the damage is so severe you couldn't fix it, but even those might be fixable if you convince a certain subset of cells that they're embryo-like or fetus-like. Then they will go in and they'll do the job that they did it once before. They can do it again.
Yeah, it's almost like the fountain of youth lies within our own cells if we know how to turn it on, basically. Yep. Right? Yep. That's what you're saying.
Well, we know it does because, the babies come from adult cells.
Exactly, right. Exactly. But most people don't think, I could, if I'm 80 years old, I can take a cell of mine, turn it into a younger cell, and then reprogram it to become a younger me. That's just not in people's framework.
Yeah, and so we even do this every day in the lab. Is most of the stem cells that we use in the lab are from my left arm. So we took skin cells, we reprogrammed them, and now they're used in labs all over the world. And we can make little things that look like embryos or like organs, and they do a lot of developmental biology in the Petri plate
on your cell, on your cells.
Well, it doesn't necessarily help me. We're not putting them back into me. But we could someday develop either person-specific, personalized cells, or we could develop generic cells that could help everybody without further modification. And that might be more cost-effective, but it's going to be a little more challenging technically.
Amazing. It's really quite amazing. I mean, the whole framework of gene therapy is just wild. And I think what I wonder is, you did this study in your lab where you used a small number of gene therapies to target like 5 more diseases of aging. What did you find in that research? What were the results?
Right. So we've published 4 papers on different ways of delivering and different genes that are being delivered. So there's like the 2 main delivery methods are using capsid proteins from AAV virus and cytomegalovirus. And the genes, I've been listing them, but in addition to the ones I've listed already, there's also follistatin and telomerase genes. All of these have been tried, and essentially all of the papers, peer-reviewed papers, have shown very significant reversal of age-related disease models. Some of them might be induced to accelerate the process because we don't want to wait even for the short lifetime of a mouse. Some have shown very significant longevity impacts. That wasn't the goal. The goal was reversing the age-related diseases, but we measured the longevity anyway, and on the order of 1.8 times longer life.
Wow! So that's a lot longer. So I'd be like living to 200 or something, right? Right. Wow, that's amazing. And so you saw which age-related diseases change?
So some of these are disease models, but there's a cardiac aortic constriction model. There's kidney failure. There's high-fat diet obesity, diabetes type 2, neurodegenerative. Our most recent one is a mitral valve disease, which is very common in a particular breed of spaniels. typically die, 4 to 6 years earlier than other dogs.
Amazing. So let's say I know you're a Harvard scientist and you can't speculate too much, but if you had kidney failure and you were about to sort of face the consequences of that, knowing what you know, what would you do? Would you take one of these gene therapies?
Well, probably that brings us to another related topic, which is I would probably take an organ, either by normal organ donor route, but there's a long waiting line, and most people that could benefit from organ die waiting, and that would probably be me as well. So instead, what's happening is we're in clinical trials now, and still some preclinical trials on organs that are transplanted from animals like pigs. So we've engineered pigs in 42 different ways, or sometimes a little bit less than that, and 42 genetic changes. And then those pigs grow up to be normal breeding pigs. So you don't have to do that every time. You get it into their germline, and then all their progeny are engineered in the same way. They're healthy, and those organs have been transplanted into primates and humans. And the longest survival so far is 600 days, and those organ recipients are still alive at 600 days. So it's looking promising. We'll be going into formal clinical trials hopefully in the next few years.
So basically the idea is you take a pig and you reprogram its genes to be like humans, so it won't be rejected, or it'll still work. And then you can put in a pig kidney or a pig heart or a pig liver or a pig whatever. And
almost every organ that we currently transplant human to human could be done with pigs.
So and this is not only bacon, we're going to get organs. Is that what you're saying?
Muscles.
That's amazing.
Yep.
That's quite amazing. So we basically, that would be an extraordinary advance, right? To not have people wait for heart and kidney transplants. I mean, ideally to get them, not having them in the first place is important. And that's what some of the other things you're talking about. How do we address the hallmarks of aging that lead to needing a new heart or a new kidney?
But not all organ failures are due to aging. So the crisis includes, accidents, workplace accidents, automobile accidents. It includes genetic problems. People are born with defective valves and so forth. So you need so there's a variety of non-age related reasons for organ failure. Yes, prevention, I totally agree, is better. Prevention will require serious medicines as well.
So from what I'm hearing, the future of aging kind of looks like this. We're understanding the root cause of aging. We're understanding these underlying mechanisms that drive all disease. And by using a whole series of strategies, and it may include lifestyle, medications, gene therapies, gene editing, we're going to be able to kind of program us to be younger. We'll be able to actually avoid those diseases in the first place. But you're also talking about how, and if we get them, we'll be able to sort of turn back the clock. We're also talking about if people have already, run out the clock and have burnt out their organs and burnt out their joints, that we're going to be able to print new ones, create new parts in ways that we haven't even been able to imagine before. And that even the 3D printing of organs is another thing I think you're working on, right? Not just
but that's much further behind than the pig. The pigs are already in clinical trials. The 3D printed organs are not fully functional for most of them. Yeah.
So the transplantation has been done in humans, is what you said, not just animals for the
That's
pig.
Correct. There's two that I know of, two human trials that there weren't really formal clinical trials. They were just individual humans. One was already on life support, brain dead, and the other one was lasted for 2 months. So the survival in the preclinical animal non-human primate trials is 600 days. In humans, the record, I think. Well, actually, the record not for pigs, but for chimpanzee to human, which is no longer really ethical. But back in 1963, the record was 9 months for survival. Yeah.
That's amazing. So how does aging look in 5, 10, 20, 50 years? How will this be transformed? How will our approach for medicine? How will our therapies be different? What's kind of coming down the pike?
Yeah, I don't think it's out of the question that we will have one of these general age-related disease reversal cures in out of clinical trials, meaning approved by the FDA for general use for at least one disease. And if it works for all diseases, and it's approved for one, then it's a very simple process to then try it for other diseases, because it's an approved drug. It makes the further clinical trials much easier. So I wouldn't be surprised if that happens within the next decade. I think the organ transplants is going to be much more powerful than we even think, because it's not just about dealing with the crisis of donors, absence of donors. It's also, we can make enhanced organs. We couldn't make enhanced organs in humans because it's just not ethical, but we can make them. So by enhanced, I mean that are resistant to pathogens, resistant to various immune diseases, possibly tolerant to a series of other drugs we'd like to produce by changing their immune system, senescence resistant, cancer resistant. We know how to do all of these in animals, germline, but we can't do germline in humans, and we can't do human to human transfers of engineered organs. So this is the way to get enhanced. We could have like enhanced all the blood cells, white and red blood cells. Wow. Could be by getting engineered hematopoietic stem cells, either from human stem cells or from pigs.
It's like getting a software update, right? It's like get the newest version,
right.
Better version, more powerful, more features, right? That's pretty wild. And in a way, it's it's a little bit sci-fi, because you're not talking about just keeping us the status quo. You're talking about actually helping evolution go faster. Like
it's not classical evolution, which is via your children. It's more like cultural evolution and technological evolution, and almost a huge fraction of our technologies are enhancements. If you think of cars, jets, cell phones, you name electric, all sorts of electric lights and so on. These are enhancements relative to our ancestors, and I think this will be the era of biological technologies.
Well, it's pretty exciting. I hope we stay alive, you and I, long enough to actually take advantage of it. And that brings us
we're already taking advantage of it. I mean, you probably took the gene therapy vaccine, right?
Yeah. Well, I did the J&J one, but yeah, that's what I got at the time. But yeah, for sure. But I think in terms of optimizing our health, longevity, it seems like there's sort of like the low tech, which is what really is profoundly effective, but it only take us so far, maybe to 100. We're talking about these other features of longevity research that are going to maybe take us to 200, or maybe actually to what you call longevity escape velocity. I'd love you to talk about what that means. Is it real? Like, what are the sort of scientific advances around that now, and how close are we, and should we even be bothered? Because what's going to happen when we never die? Because what makes us human is that we have mortality, and why the gods were so upset in Greek mythology is that they never died.
Yeah, I don't think that mortality necessarily is the defining feature of humanity. I think it's more about our ability to reflect on the past, even ancient past, and to use that to help us plan the future. I think that's really one of and also caring for other human beings in a way that goes beyond normal paternal and fraternal caring. So I don't think that's humanity is at risk here. Before I talk about escape velocity, I just comment on the 100. Yes, we can get to 100 if we live very well and if we're lucky at the genetic lottery. But most people, when they get to 100, even the centenarians, are not very youthful, honestly. We kind of celebrate their 100th birthday, but, they're usually, sitting down and not running around the room like a kid would. They're not, they're not doing backflips and black diamond skiing. Usually, there may be a few exceptions, but we want to have the average 100-year-old be very youthful, so that there's no doubt in their mind that they feel the way they did when they were 25. So, in a way, that's to some extent that's more important medium-term goal than escape velocity. Now, escape velocity will probably follow from that. If you can get a 100-year-old to behave like a 25-year-old, you probably solve the problem. It doesn't mean you will live forever. I mean, there's still, the sun's going to explode and, or turn into red, and
that's a few billion years down the road.
Yeah. I mean, there are all kinds of things. Maybe thousands of years from now, there'll be an asteroid. But anyway, I think if we get to the point where we can reset a 60-year-old to 30, then we're probably, when that 30-year-old, that new 30-year-old becomes 60, we'll reset it to 30, and we might be there. So that's a good goal. And now, then, I mean, I think you're raising the ethical point of what happens when everybody keeps resetting from 60 to 30 forever. Some people worry about population explosion. I think there's a subset of us that worry about population implosion. That is to say, if you look at current demographics, everybody is moving to cities. I mean, somewhere between 65 and 80% of us are in cities, and it could be 97% soon. And when they move to cities, they change their goals for procreation from about 7 children per family to about 1.2. Now, 1.2 means implosion. It means population keeps shrinking over long periods of time. So, and then another source of possible population reduction aside from death is immigration. So it used to be that there would be a drain of people from Europe into America. Now there's going to be a drain of people from Earth to elsewhere. And so we have to think about those two things, the urban reduction in fecundity and the fact that there is a big universe out there that we might be wanting to participate in, if nothing else, to have a backup for Earth. Not because we're going to pollute Earth. Maybe Earth will do just fine, but we want to have a backup that saves us from asteroids and solar flares and all the rest.
Yeah, well, I mean, I don't know if I want to live on Mars.
Well, you don't have to. I mean, because it's like most of the people stayed in Europe. It was just the crazy, brave, the ones that had a different religion, that conflicted with it. Those are the ones that went to America, or the prisoners. It doesn't have to be everybody, but the point is, it does drain the population.
Yeah, amazing. Wow. So I mean, we're like almost at 8 billion, but we were, I think we were at 1 billion ish at the turn of the 1900s. So we've gone up quite a bit. I think we have room to go down. Might not be a bad idea.
Well, yeah, we also have room to go up without getting off the planet. I've estimated that we can probably handle 20 billion if we used our farmland differently. I think we could. Right now, a typical human uses a typical vegan human might use 9 acres of land, and then if you're really into beef as your sole source of food, it's going to be maybe 10, 20 times that. So I think it could fit into the size of your house. You could have a footprint which one small house is enough to produce all the food you need for a small family. So
clearly, I'm sure agriculture isn't your expertise, but it sounds like the conversation around protein and aging is an interesting one, and you're sort of implying something there, both in terms of planetary health, but also in terms of longevity. And I know a lot of people in the longevity field are talking about reducing animal protein to actually help keep mTOR quieter and help autophagy and the recycling of proteins and cells and the cleanup crew, so to speak, of our system. I'd love to hear your perspective on that, because I think I have sort of maybe a little bit contrarian view, and I'd love to hear what you're thinking about it and chat about it for a minute.
Yeah, we
basically having more protein or less protein as we age, and what about animal versus non-animal, and how does that implicate itself in all the hallmarks of aging?
Yeah, so I may have a different contrarian. We may both be contrarian, but slightly different. But the first thing I want to point out is it's not a one-size-fits-all thing. It's not that everybody that ages needs to increase or decrease their protein. It's that some people are born or become allergic to certain kinds of foods as they grow up. So there are people that are extremely sensitive to lactose. There are people who are very sensitive to fructose and other diabetogenic, more so than the average. There's MODY is a highly predictable genetic predisposition to diabetes. And the list goes on. There are people that are actually allergic to animal proteins. They can't handle the sugars that are on the surfaces of the of non-human animals. So, and the list goes on. So you need to be aware of your genetics. A lot of us are very, self-righteous that we're healthy because we eat well and we exercise, but we also won the genetic lottery. And so we need to be very cautious about all the other people around us who can't get the same thing. So that's one thing. I think that animals are very problematic for a lot of people because they increase cholesterol. And that alone is a problem. But in addition, they have planetary problems like use of antibiotics. I mean, that could be regulated, but it isn't as well as it should be. Use of fertilizer runoff, water, zoonotic diseases. I think we're pretty sick. We're pretty tired of zoonotic diseases right now. I think we've had our fill since COVID was one. Wasn't necessarily due to farming though, but it illustrates the point. Is a lot of our influenza comes from domesticated animals. In fact, an alarming statistic is that 96% of mammals on the entire planet, not just in the industrialized nations, 96% of mammals are either us or are domesticated mammals. 96%. And that could change in a snap, because there are plenty of people who, survive their entire lifetime on a vegan diet. There's all kinds of great recipes that are as good or better than anything you normally eat from animals. So that would shrink the land usage, water, fertilizer, zoonotic diseases, and for the subset of people who have a cholesterol problem. I'm not saying this is everybody. Again, personalized food.
You're talking about conventional feedlot, animal agriculture, not regenerative agriculture, right?
Yeah, I'm talking about whatever agriculture works for vegans. There are a variety of ways of doing it that are healthy, and you need to monitor them. You need to make sure that they don't have infectious diseases, for example. So there are some infectious diseases that get in through organic farming as well as non-organic, inorganic, I think almost every way you grow animals has a risk of zoonotic diseases and cholesterol for the subset of people that have a cholesterol problem.
Yeah, I mean, the thing about saturated fat that's in animals mostly is stearic acid, except for what's in butter and milk. But stearic acid in meat doesn't actually impact your cholesterol levels.
I wasn't talking about stearic acid. I was actually talking about cholesterol.
Right, but stearic acid is the saturated fat in meat. I don't think it raises cholesterol. It actually.
I agree. I'm not. I got nothing against stearic acid.
Yeah.
I have something about cholesterol. In fact, I have an inherited problem with cholesterol. That killed my father. So, and there are people that have even more severe cholesterol problems than I do, called hypercholesterolemia. Yeah. So that's what I'm talking about. The cholesterol molecule, which looks very different from fatty acids. It's not a fatty acid at all.
For sure.
It is a fat, though.
Yeah, for sure. Yeah, I have an inherited cholesterol problem too. It's based on absorption. I kind of am a hyper absorber. So interesting. I had a lot of heart disease in my family, but I would imagine that 500 years ago there wasn't any heart disease in my family. It was. I mean, you read the reports from William Ulster and Johns Hopkins.
Only 500 years ago, you had a similar situation to what poorer people have in the world today, which is they don't have the luxury of eating so much meat.
Yeah,
and so the solution to the cholesterol problem was poverty back then. But I don't think that's I think if anything, we should be trying to eliminate poverty, and yeah. Anyway, so
Well, what about protein aging specifically? Because, from my understanding, that sarcopenia, which is loss of muscle, hugely contributes to all the disease of aging. It drives inflammation, hormonal dysregulation, lipid dyslipidemia, insulin resistance, just creates a whole cascade of problems. Low growth hormone, high cortisol. And that's really driven by inadequate muscle building or synthesis, which partly comes from exercise, but the quality of the protein really matters. And if you look at the data, it really matters to have higher leucine levels in protein in order to activate protein synthesis, because it's a rate limiting step. So if you have plant protein as you get older, and even the studies that show that animal protein may be harmful when you're younger shows that it's better when you're older to build muscle. So how do you thread that needle? Assuming we could, figure out a way to either have, cell meat, or we could have regenerative agriculture, which is a different profile and so forth. It may not have the same impact, maybe actually reduce climate destruction, and may have better fatty acid profiles and better phytochemicals. Let's just say, for that argument, we could actually eat animal protein as we get older. What's the science from your perspective on how to manage this mTOR problem? Because too much stimulation of mTOR with extra amino acids or sugars causes sort of an overproduction of proteins and inflammation and a lot of downstream consequence of aging, and not silencing it will lead to lack of autophagy or cleanup, and which is so critical to the longevity process. So how do you kind of thread that needle? I think people are really interested in hearing a debate about this.
So I've studied amino acid metabolism in plants and animals. In fact, I was a guinea pig in a study at MIT on a leucine deficient diet, a model for kwashiorkor. Probably not a smart idea, but I was a teenager at the time. But anyway. So that's why I'm have brain problems. I'm just kidding.
I think you're doing all right.
Anyway, I think that from my study of plant of the literature on plant amino acids, they can, with the right diet, they can be more or less identical to the amino acid composition of a meat-based diet. So there's no fundamental problem with making a vegan equivalent in terms of amino acid composition. And
how would you do that other than adding extra leucine to the proteins, or having?
There are plenty of plants that are leucine rich. It's also plant parts, so it's not like you have to eat the whole plant. There's particular seeds that have more leucine than other seeds. The seed stores proteins vary tremendously from plant to plant. So, if you want, I can send you some links to specific sources of leucine from plants. But it's not just about leucine. The point is, you can perfectly mimic the profile if that were mapped. Now, I think that most Americans get an excess of proteins, and so they pick and choose what they need. And so, as long as you're above the minimum. But ratios do matter. I don't want to diminish that, but broadly speaking, we have a good diet, and I think that no matter how you grow the animal protein, you still have the problem of cholesterol and zoonotic diseases that just.
Yeah. But I mean, for example, for you,
the other Earth problems, but you have those two human medical problems.
But in terms of the should we be eating more protein as we get older? Do we need, do we need it to maintain our muscle mass? How does that play a role?
I think that varies from person to person. Some people never get sarcopenia, and other people, have genetic problems with too high of protein. Some people can deal with the Atkins diet. Other people get ketogenic.
Right.
So it has to be crafted, but I think to a first approximation, a modest increase in protein is achievable with a vegan diet.
Yeah, amazing. Okay, so that's fascinating. I want to just sort of close with one of your amazing projects called Colossal Bioscience, which is a company that's trying to bring back, since the woolly mammoth, through editing the genes of an Asian elephant. And you talk about it being, both of scientific value, but also that it might even help us save the planet. So can you talk about that project and what you're finding and where we're at with it? Because it sounds kind of wild and a little bit of a distraction from your normal work.
I'll try to connect the dots to some of the other things. I mean, we've been talking about reversal of age-related diseases, This is kind of reversal of ecosystem damage.
Yeah.
And most of that, I think this is a different way of thinking about the ecosystem, is we don't have to point our finger and say, oh, you're responsible because you have a smokestack, or you're responsible because you're driving an SUV. It's really 15,000 years ago, some of our ancestors were responsible because they killed off almost all of the big herbivores in the Arctic. And you say, well, what's the big deal about the Arctic? Well, the Arctic is a unique ecosystem that sequesters carbon.
Yes.
We talk about carbon sequestration, but it does it naturally.
Yeah.
Each year, you get a whole layer of grass and all the grass roots below it that freezes solid, and then dust and feces are on top of that, and another layer of grass grows, and it freezes and so forth. And so the thickness of the soil in the Arctic can be 500 meters thick, while the average thickness in most forests is more like 1 meter. And so it's much, much thicker, because in a regular, let's say, tropical forest, you're like constantly turning over that carbon into carbon dioxide. And so it never gets very thick. But that's the good news. The bad news is all of that is at risk now, because if it melts, it's all going to decompose into either carbon dioxide or more likely methane, because carbon dioxide requires access to oxygen, and most of it's going to decompose anaerobically without oxygen. And so methane is 80 times worse than carbon dioxide in terms of climate change. So anyway, we want to restore the herbivores, but the herbivores can't make it, because they can't penetrate the forests, the trees. And so elephants are one of the few herbivores that can knock down trees, and they love knocking down trees. You can look on the internet, you can get dozens of nice short videos of them knocking down trees. So anyway, that would restore the grasslands. You still have trees interspersed, but plenty of grassland for the herbivores to restore. And this experiment's been done. The ecosystem experiment has been started by our collaborators at Pleistocene Park, and we hope to have additional herbivore stations in Canada and Alaska as well. And then, as those herbivore stations are growing up, where we have to, then we'll supplement them with cold-resistant elephants. And so the same tools that we talked about earlier for engineering pigs at 42 loci, 42 genetic positions, we'll use that to make a similar number of changes in the elephants.
Because basically they make like 50 pounds of poop every day. So that helps fertilize it and grow new soil, is that you're saying?
Yep. Yeah. Well, I mean, yes, it's not the major thing that they will do, but the major thing they will do is convert some of the trees back to grasslands. And we're going to focus on the parts of the Arctic that have the most carbon already, because we want to keep that soil cold, frozen year round, or at least once a year. And when I was last in Siberia was actually the first year in recorded history that the summer melt did not refreeze. The top layer did, but there was a layer in the middle that didn't refreeze. So that's an ominous milestone.
How close are we to having your gene-edited elephants up in the Arctic and new woolly mammoths?
So, it's a similar timeline for how close we are to clinical trials for the pigs. Well, the pigs are already in clinical and preclinical trials. Elephants are probably, the first calf is probably 6 years away. That's at least the goal. And that includes a 22-month gestation period. So this is the longest gestation period of any mammal that I know of. And so that's, but another 4 years for working out ways of scaling up the gestation outside of the elephant body, starting with other mammal gestation.
That's really incredible. What is your top things to do in looking at extending your health span and your lifespan, so you both live long and healthy? And what are the things that we now know that we should be implementing? I mean, is it rapamycin, metformin, NMN? Is it, obviously the lifestyle stuff, but what are you kind of seeing as the most promising advances right now?
Well, I think most of them, kind of how we started, is people know, and it's just a matter of whether they are willing to do it or not. So it's getting a lot of exercise, having loving relationships with friends and family, eating well. I would say a vegan diet, but it can be whatever works for you. And above all, knowing yourself, knowing how you're different from other people. Just don't assume that if you have the diet book that tells you, how everybody should have the same diet.
Yeah.
I would take those with a grain of salt, and I would learn your genome, get your genome sequenced. There might be something lurking in there that could affect you or your kids. What does it hurt to learn a little bit? Maybe you get one of your friends that's a little geekier to explain it to you the way they explain your computer. But the point is, it's not that hard. And physicians are getting better and better at understanding how each person is different. There's revolution in personalized and precision medicine. Tune into that. That's probably the best thing you can do for yourself, assuming you're already following all the other ordinary things you can do for yourself.
And how about you? Are you taking supplements? Are you taking NMN? Are you taking metformin, rapamycin?
I think that
you don't have to answer that, but you can.
No, I'm happy to answer it, but I think it's important to say it's not important. It doesn't matter what I'm doing. I'm a guinea pig, right? So I'm taking things that aren't necessarily recommended for other people. I've been a guinea pig ever since I was a kid. Both of my parents did experiments on me. Not all of them were approved by IRB.
Wasn't too dramatic.
And I'm the main guinea pig in my lab for ethical reasons that you don't want to do. You want to do it. You don't want to perceive to be coercing employees, right? So they do experiments on me. That's fine, or on my cells more frequently. Anyway, so I don't recommend any particular thing other than the dietary things that we talked about before. I think that there will, partly because this whack-a-mole thing we talked about most of these supplements just address one or two of the 9 or 10 hallmarks of aging. You really have to get all of them to have an impact. And most of them are kind of, frankly, wishful thinking. The hope is there's a fountain of youth, something you can drink, something you can eat or not eat. And I think that's limited, except in cases where people have a particular genetic problem that they need to fix. So if you avoid phenylalanine and you're phenylketonuria, that's a good combination that's to be aware of. That's a particular dietary thing. Diabetic or pre-diabetics should be very cautious about foods that cause glucose spikes. And there's a whole science that you have to understand if you're pre-diabetic. You can't just blindly follow some cookbook.
For sure.
Anyway, that's
so that sidestepped the question of what are you doing?
I'm doing some experimental stuff that I would not want to even mention the names.
I got it. Okay.
So it's not that I'm dodging. It's not that it's it's invasion of my privacy. It's just that people have a tendency to take it as I recommend a healthy vegan diet. That's what I recommend.
So next time if I see you and you have black hair and I look 20 years younger, I'm going to go, what are you doing?
First, you'll see the black roots.
It's the opposite, right?
But hair is pretty easy. I mean, you could easily restore melanocytes, just like you could dye your hair. I mean, it doesn't necessarily mean you fixed aging.
For sure. Well, I love this conversation.
If you have fixed aging, it is quite possible that you will get restoration of melanocytes that are missing.
If you love that last video, you're going to love the next one. Check it out here. We really need to get away from the single diagnosis. Just because you know the name of the disease doesn't mean you know what's wrong with you. You could have depression, but it could be 10 different causes. Or rheumatoid arthritis and have 10 different causes. So what we want to do is have our health span equal our